lesson you talked about equilibrium constants, equilibrium law expressions, and we talked about some qualitative things with respect to equilibrium systems. So how can we determine if they're reactants favored or products favored? What kind of sense do we get about the equilibrium position based on the equilibrium constant? But we don't really know how to do quantitative things yet. What if I put in a certain amount of reactant and no product, and I want to figure out where the equilibrium position is going to end up? So how many moles of reactant will I be left with? How many moles of product will be formed? I can't use the stoichiometry that I learned in Chemistry 20 to do this, because that stoichiometry requires a reaction to be quantitative. It requires a reaction to go 100%. 100% of the reactants are converted into products. And for these equilibrium systems, we know that they are not 100%. That's what makes them unique. That's what makes them an equilibrium system. So we're going to need a new system here. And the system that we're going to use is called an ice table. Stands for initial, change, and equilibrium. And I'll show you how to make one of those. Now note, if you have a quantitative reaction, you don't need to use an ice table. You can use the same basic vanilla stoichiometry that you learned in Chemistry 20. Here though, we need a little bit more. So how do I make an ice table? So let's take a look at this example. Consider the reaction equation for the formation of hydrogen iodide at 448 degrees Celsius. Now, you'll typically be given a temperature not because you have to do anything with it, but because if the temperature changes partway through the reaction, then the equilibrium position will also change and the math won't work. We're going to assume the reaction has begun with 1 mole per liter concentrations of both hydrogen and iodine gas. Construct an ice table to determine the equilibrium concentrations of the reagents. The equilibrium concentration of iodine, determined by color intensity, was 0.22 moles per liter. Okay, the first thing I need to do is I need to write out my equation. So we're being told that this is the formation of hydrogen iodide from hydrogen gas and iodine. So the equation is going to look like this. Note that it's balanced. An ice table will only work with a balanced chemical equation. Then I'm going to have 3 rows here. The first is going to be my initial concentration. Then I'll have my change, which is also moles per liter. And then I'll have my equilibrium concentration. Which is also measured in, you guessed it, moles per liter. And this gives me sort of a grid. I know some of these values, but I don't know all of them. So let's see what we know. My initial concentrations of both of these reactants were 1 moles per liter. And I'm not told what my initial concentration of my product is, but for these types of questions, if you're not told what your initial concentration of your product is, you can assume that the initial concentration of the product was 0. Because if there was something there, we would have told you about it. So my initial concentration of my product, then we can assume, is 0 moles per liter. Then what else do we know? We're also told that the equilibrium concentration of the iodine was 0.22 moles per liter. So my iodine here, I know this equilibrium concentration, 0.22 moles per liter. And that's all that I'm told. I'm not told what my equilibrium concentrations are for my HI or for my hydrogen, and I'm not told directly what the changes are. But the change row is just telling me what the difference was between what I started with and what I ended with, right? And for my iodine, if I start with 1 mole per liter and I end with 0.22 moles per liter, well then my concentration has decreased by 0.78 moles per liter. So the change was negative 0.78 moles per liter. And I can, and once I know one of the changes here, then I'm set, because I can figure out the change here and the change here, making sure that I pay attention to the coefficients. So this is why my equation needs to be balanced. So my iodine and my hydrogen, they react in a 1-to-1 ratio. So if my iodine decreases by 0.78 moles per liter, my hydrogen will also decrease by 0.78 moles per liter. And my hydrogen iodide is going to increase because it's a product, right? These are reactants that are being consumed. The product is going to be produced. But it's not going to increase in a 1-to-1 ratio. It's a 2-to-1 ratio, because there are 2 moles of hydrogen iodide produced for every 1 mole of iodine that are consumed. So if I'm consuming 0.78 here, I'm going to produce twice that, which will mean that this guy is going to increase by 1.56 moles per liter. And then, now that I know all of the changes, I can fill in this concentration row for the ones which I don't know yet, right? So for my hydrogen, it started at 1, decreases by 0.78, so it's going to end up at an equilibrium concentration of 0.22 moles per liter. And for my product here, my HI, it started at 0, it increases by 1.56, so 0 plus 1.56 is 1.56 moles per liter. So then I'm done. My job was to figure out the equilibrium concentration of the reagents. So to make it nice and clear what my answers are, I would say my equilibrium concentration, I can use my square bracket to represent concentration, of my hydrogen gas equals 0.22 moles per liter. And for my product, my hydrogen iodide, my equilibrium concentration is, we get 2 significant digits here, so 1.6 moles per liter. And these are my final answers. Let's do another pretty straightforward example. I have a 500 milliliter stainless steel reaction vessel at some temperature. Carbon monoxide and water vapor react to produce carbon dioxide and hydrogen. So let's write down my reaction while we have it fresh up here. So carbon monoxide gas and water vapor, so that's a gas too. They react to produce carbon dioxide. And hydrogen, don't forget, that's diatomic. Let's look at my balancing here. I've got 1 carbon, 1 carbon, 2 oxygens, 2 oxygens, 2 hydrogens, 2 oh, so that's balanced already. That's nice. Evidence indicates that this reaction establishes an equilibrium with only partial conversion of reactions to products. Initially, 2 moles of each reactant is placed in the vessel. Kc is 4.20, and what amount concentration for each substance will be present at equilibrium. Okay, let's build my ice table. So initial, change, equilibrium. Everything here is going to be in moles per liter. So I started with 2 moles placed in a ½ liter reaction vessel. So I have to watch, because I have to plug in a concentration here. Concentration isn't 2. Concentration is 2 moles divided by ½ liter, so that's actually 4 moles per liter, right? So for each of my reactants, my initial is going to be 4 moles per liter, 4 moles per liter here. It doesn't tell me that we put any products in, so again we can assume that each of these is a 0. Now, I'm looking for the amount concentration of each substance at equilibrium, but unlike the last one, I'm not given any of the changes, so I don't know what these decrease by. I don't know what these increased by. But I am given another piece of information, which is the KC. So the KC is going to come in valuable here. I'm going to have to do a little bit of algebra. So let's first write out my equilibrium law expression. So it's going to be the carbon dioxide concentration multiplied by the hydrogen concentration divided by my carbon monoxide multiplied by my water vapor. Those are all gases, so they all get included. If this was liquid water over here, it wouldn't get included, right? Now, I don't know any of my values here. I do know my value for Kc at 4.20, so I'm going to need to do a little bit of algebra here. Now, because I don't know any numerical values for the changes, I can use a variable x. So I'm going to say I know that these reactants decrease. I don't know by what, but I know that they decrease by some value, and they decrease in a 1-to-1 ratio. So if this guy decreases by x, this guy will decrease by x too, or x as well, right? And my products, they increase by some value. They're produced in a 1-to-1 ratio as well. So my carbon dioxide will increase by x, and my hydrogen will increase by x. Then in the equilibrium row, again, I don't have a numerical value yet, but what I can do is figure out what I can do is I can figure out how my x is going to factor into this. So I started at 4, I decreased by x, so my equilibrium value here is going to be 4 minus x, whatever x is. And that's going to be the same for my water, 4 minus x. These guys are 0 plus x, so they're just going to be x and x. Now, what I can do now is I can plug in my equilibrium terms into my Kc, and I can solve for x. So, this is when the math gets really good. So, here's my products. They're on top. So we have x multiplied by x. Right, that's my carbon dioxide and my hydrogen. And then that's divided by 4 minus x times 4 minus x. Now this seems a little bit scary, but we haven't made it that bad on you, because if you recognize that 4.20 is equal to, well, x times x is x squared divided by 4 minus x times 4 minus x would be 4 minus x squared. Then I can recognize that the right side of the equation is a perfect square, right? I've got a square divided by a square. So I can get rid of these x squareds by square rooting this whole side, as long as I square root this whole side here too. And this is going to make my life a lot easier than if I had foiled out this bottom here and tried to collect the x's. Yeah, I'd still be able to solve that way, but you're going to have to use the quadratic equation if you do it that way. This way is going to be a little bit easier for you. So if I square root and square root, then let's take my next step over here. So I'm running out of space. Then the square root of 4.20 is equal to x divided by 4 minus x. So we can fire on the trusty TI-83 here, and let's start to do a little math. So I need the square root of 4.20, which is going to give me 2.05. So let's replace that here. And I'm going to save all those digits. So I'm going to put an ellipses here, dot, 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 which means that I'm tracking those digits that I have. Then I need to collect my x's. So let's multiply by 4 minus x on both sides to get the x's up to the top of the fraction. So we can multiply by 4 minus x here, can multiply by 4 minus x here. These guys are going to cancel, and then that'll give me 4 minus x times 2.05 is equal to x. We can multiply this guy in. So my 2.05 times 4 gives me 8.19, again, and some change. And then we'll subtract 2.05 x. And that's equal to x. So then to get the x's together, we can add 2.05x to each side, plus 2.05x, which will give me 3.05 x, right? Because we're adding another 1x to it. And that's equal to 8.19 with its change. Finally, we can divide by 3.05. Those guys will cancel, and x will equal my 8.19 divided by 3.0, which gives me 2.688 as my value of x. Now, you have done a lot of work here, and so you're tempted to just sign off on this bad boy and say I'm done, but you haven't actually answered the question yet. We figured out the value of x, but we have to sub this x back in here to figure out what my specific concentrations are going to be. So let's look first at how many sig digs I'm going to get. We had 3, so we get 3 sig digs. So let's round my x value, 2.68, so this will round to 2.69. And then I can sub back in for my products quite easily, right? Here's my carbon dioxide and my hydrogen. So what I'll say down here is my CO2 equilibrium concentration. It's just going to be 2.69 because it is just x. And the units are moles per liter. Same with my hydrogen. My hydrogen is 2.69 moles per liter. For my carbon monoxide, 4 minus x is my equilibrium concentration. So I need to take 4 minus my x value, which will give me 1.31 for my carbon monoxide moles per liter. And for my water, the formula is the same. (1.31 moles per liter). And then these guys here are my final answer.